Check this out. We've got something really fun today. This is so amazing. Oh man, again? 11.1 and 11.2, Counting Methods, Part 3. Let's look at the words and or using this example here. There are 5 women and 4 men to choose from for a committee. How many ways can a committee of 4 people be chosen if gender is irrelevant? So we would have 9 people, and we would want to choose, so make a combination with 4 of them. And this is just the most basic question. As a review, it's just 126. What if there must be at least 2 females? So if it says at least, then we could have 2 females, or we could have 3 females, or we could have 4 females. And that would be all 4 females and fill up this committee. So if we have 2 females, we must have 2 males to fill up this committee. So 2 females and 2 males. If we have 3 females, we must have 1 male. And if we have 4 females, we'd have 0 males, and we can put that or not. It won't make a difference mathematically. So for 2 females, we've got 5 to choose from, and we want 2 of them. Now the word and is going to mean the fundamental counting principle. We have this many ways to select the females, and this many ways to select the males. So we got 4, choose 2. But the word or here is not the fundamental counting principle. It means that we've got this thing happening, or we've got this thing. And so or translate into math in these questions as addition. So then we go on, fill out the rest of this question. So 3 females is 5, choose 3. 1 male is 4, choose 1. And then the or is a plus sign here. And then 4 females is 5, choose 4. Now you can put the males in here. Won't make a difference again. If you put 4, choose 0, there's only one way to do that, and it's just 1 there. So it doesn't affect the question. All right, let's actually put these numbers in the calculator. We get that this is 60, and this part is 40, and this part is 5, meaning that there's 105 ways to make a committee with at least 2 females. What if the committee must be all men or all women? So we'll say all men. That would be 4, choose 4. Or all women. And the or is a plus sign here. And then we'd have all women would be 5, choose 4. And 4, choose 4, well, there's only one way to do that. And 5, choose 4 is just how many ways can we leave 1 woman out. So that's 5 ways there. And this is just a total of 6. How many ways can we line up 5 people, Apollo, Zeus, Odin, Thor, and Loki, for a picture if there are no restrictions? But first of all, we're just lining up 5 people, so that would be 5 factorial. You could also write this as making a permutation with all 5 people. These mean the same thing, and in either case, this is just 120 different ways. What if Apollo and Zeus must be on separate ends? So you have 5 people, 1, 2, 3, 4, 5, and Apollo and Zeus need to be on the separate ends here. So that means that there's 2 ways to do that. They could switch places here, or 2 factorial or 2 ways. That leaves the 3 people in the middle. And so there is 3 factorial ways to arrange the 3 people in the middle. So 2 factorial times 3 factorial is 12 ways. What if 2 of these 3 people, Apollo, Zeus, or Loki, must be on the ends? Well, there's a bunch of different ways to do this question. First, let's just make 5 blank spaces here. 1, 2, 3, 4, 5. And we'll just go through it one by one. First space here, how many choices do we have for this space? So there's 3 guys here, so we have 3 choices. Now, when we're using the fundamental counting principle like this, we need to go take care of all the restrictions. So the first one and the last one have restrictions in this question, and then we can do the middle ones. So make sure you do the restrictive blanks first. Now, if there was 3 choices here, we used up 1 guy, we put it here. So at the end, there's only 2 left to choose from. Now, we used up 1 more guy. So bringing the other 3 into the middle here, we've got 3 to choose from to fill in this blank, 2 to choose from here, and 1 to choose from here. And this is fundamental counting, because we calculated how many ways to do each of these things. And we multiply this together, and we get 36 ways. We can also do it a different way. We could say that there's 3 of the guys here, so 3, and we want to choose 2 of them to be on the ends. And then those 2, we're going to make an arrangement with them, so 2 factorial. And then the 3 remaining guys is 3 factorial. And so this is also, of course, 36. Now, let's do it a different way. What if we had 3 guys and we're going to make a permutation with 2 of them? And so that will take care of this and this in one step. And then we've got 3 guys and we're going to line them up. And 3p3 is just the same as 3 factorial. And we multiply this out and we get as well 36. And another way you might consider this question being there is a beginning and an end. So begin, end, and middle. So these 3 guys are going to be put in these 3 positions. 1 at the beginning, 1 at the end, and 1 put into the middle somewhere. Not the literal middle, I mean middle 3. Okay, so that would be 3 factorial. And then the 3 middle would also have 3 factorial ways to do that. So 3 factorial times 3 factorial is again 36. Now I guess I'll number these because we did 4 different ways to solve this question. You can see that there's a lot of options. As long as you're thinking about the question in the right way, you should be good. How many unique ways is there to arrange the letters in accesses if we must begin with exactly 2 S's? So there's 8 letters here, so we'll just draw this out. 1, 2, 3, 4, 5, 6, 7, 8. And we want to begin with exactly 2 of the S's. Now that means that this one cannot be an S, or then we begin with 3 S's. So what does that leave us? It leaves us with starting with an A here. We could start with a C in the second position, or an E. And that's all of our options here. And then the other ones can be S. So this one will just be rearranging the remaining letters. So this would have a C and a C and an E and an E and an S. And if we used a C here with the 2 S's in the front, we would just be left with an A, a C, an E, and an S. If we did SSE, then we would have an A here, 2 C's, another E, and the last S. Okay, so now we can calculate each one of these. So this here is 5 factorial because there's 5 letters we're rearranging. There's 2 C's and there's 2 E's. So that would be 30. For the next one, there's also 5 letters and there's 2 E's, and that's all that repeats in this one. And for the last one here, there's still 5 letters and we have 2 C's, and that's all that repeats in this one. So think of this, we could put an A here, or a C, or an E. So if we have OR, that means we're adding these three. So we've got 30 plus 60 plus 60 is equal to 150. Let's try this question a different way. Let's say we had 1, 2, 3, 4, 5, 6, 7, 8. We started with our two S's, and there's 6 letters here, so a total of 6 factorial divided by 2 factorial for the 2 C's and the 2 E's that we have here. So this is the total number of ways we could rearrange the remaining letters, but we don't want the S showing up here. So we can subtract off the number of ways that S shows up here. So if S shows up here, then we just have these remaining letters here, and that would be 5 of them, and 2 of them would be C's, and 2 of them would be E's. And if we do this, this is 180, and this right here, we've already calculated, it's 30, and we still get the same answer. Now this one we had to go through 3 cases, and this way we just think of the overall and subtract off the case we don't want. So perhaps you prefer this approach here. Now the next one, we must begin with at least 2 S's. That means we could have 2 S's or we could have 3. That's actually this case right here. It means we don't care what's happening, so it's just 6 factorial over 2 factorial. 2 factorial is 6 letters left after the 2 S's are in front. Shuffle them around. Who cares if the S comes next or not? And this is just 180. How many 4-letter arrangements can be made by taking 2 letters from the word dart and 2 letters from the word foils? Now you notice that they don't share any letters, which is very nice. We need 2 letters from the word dart, and we have 4 unique letters to choose from. So first I'm going to choose the 2 letters from this. Then I'm going to do the same for this. So, and there is this many ways to choose 2 letters from the word foils. Now that I have those 2 letters from each of these words, I need to rearrange them to make another 4-letter arrangement. So that would be 4 factorial, or you could do 4 permute 4. And this is it, 1,440. There are a certain number of dots, no more than 2 of which are collinear. Each dot is connected to every other dot with only 1 line. If 55 lines are drawn, how many dots are there? So let's start off by drawing some simple examples and then seeing if we can observe a pattern. So if we have 3 dots, then they might be arranged something like this. And there is 1, 2, 3 ways to draw lines that connect those 3 dots. Let's try 4 dots. They might be arranged something like this, and there's 1, 2, 3, 4, 5, 6 lines that connect those 4 dots. Let's try 5. 1, 2, 3, 4, 5. And there'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines that connect those 5 dots. So you might notice that in each of one of these, we have a certain number of dots here, in this case 3, and we're just choosing 2 of them to draw a line in between. Now the order that we draw the line doesn't matter, so that's why we're using a combination here and not a permutation. This one would be 4, make a combination with 2 of them. This one would be 5, make a combination with 2 of them. Now obviously we could just draw this out to 55, but let's do it the algebraic way. So we're doing combinations, but we don't know the number of dots. So that will be x. So let x be the number of dots. That would mean we have x, choose 2, and that's going to equal 55. Now break this down into its formula. We have x factorial over x minus 2 factorial times 2 factorial is equal to 55. Now the first thing we can do is get rid of the 2 factorial because it's just equal to 2. So I can multiply both sides by 2 and get rid of that. Next we have x factorial and x minus 2 factorial, and we really need to get rid of the factorial. Now x factorial is larger than x minus 2. I mean, x minus 2 is 2 less. So we need to peel off terms from this one until we match this one. So the first term of x factorial is x. The next term would be 1 less, so x minus 1. Since I don't know what x is, I just have to write x minus 1. The next term is x minus 2, and it would go all the way down to 1. But I want to stop here because this actually matches what our denominator is. So I'm not going to go all the way down to 1. I'm just going to write factorial here, and this one was already factorial. And now I can cancel the x minus 2 factorials. And 55 times 2 is 110. And now I'm just left with a quadratic. So x squared minus x, bring this to the other side. And I can solve that quadratic to find x. I can solve it by factoring, in this case, x minus 11, x plus 10, and that would give me that x is equal to 11 and negative 10. Now, if we're choosing items here from a group, we can't have that group have negative 10, so that doesn't make sense. So our answer is 11 dots would create 55 lines. A combination lock has numbers 0 to 39. If a combination uses 3 numbers, how many combinations are possible? So the order matters. You can't just put the 3 numbers in your combination in any order and the lock will open. So first thing is, our combination lock is actually a permutation lock. How many ways are there if we need 3 unique numbers? So we could use fundamental counting to find this. There'd be the first digit of our combination, and our second and our third. And we could just multiply that. How many options are there? Careful with this question because we include 0 here. So there's actually 40 options for the first number. We used 1 up and we can't repeat it, so 39 options for the second and 38 for the third. And that's 59,280. But this is just a permutation, and we have 40 options, and we're making a permutation with 3 of them. So this also equals 59,280. What if the numbers may repeat? Then we'd have 1, 2, 3, and each time we'd have all 40 options. So this would just be 40 cubed, which would be 64,000 different so-called combinations. If we are arranging these 7 letters, how many arrangements can we make if we must begin with an A and end with a vowel? So I'll make 7 blanks here. 1, 2, 3, 4, 5, 6, 7. The A needs to go here, so there's only one way to do that. Since the A is used up in the first position, that leaves us with 3 vowels for the end position. And the 5 remaining letters fill in here. And if you'd rather just write 5 factorial, that would be great. We multiply these together, we get 360 ways. What if we begin with a T, 1, 2, 3, 4, 5, 6, 7, and there's only one way to do that, and end with a vowel this time, but we have all 4 vowels available, so this would just be 4 instead, and all of these would just be 5 factorial to arrange the 5 remaining letters. So 5 factorial times 4 is 480. A rugby team with 7 players and 2 coaches are lining up in 2 rows for a picture, as shown below. Coaches must be at the ends of the top row. How many arrangements are possible for the picture? So let's deal with the coaches first. They need to be here and here, but they could switch, so that's 2 or 2 factorial ways for them to be arranged. The remaining 7 players can be arranged in these 7 positions. So that would just be 7 factorial. And this would be a total of 10,080 arrangements for this team. 5 people are going to book seats on a flight where there are 8 available seats left, as shown in the diagram below. How many ways can they be seated? Now, we see that each one of these seats are unique, and each one of these people are unique. So we don't have any repeating items, and we've got 8 seats to choose from, and we're going to make a permutation with 5 of them. And that's it. This question would be 6,720 possible ways they can be seated. For this question, we want to solve for n. So we need the combination formula. That would be n factorial over n minus 2 factorial times 2 factorial, and that will equal 28. Now you could just graph this in your calculator and get the answer, but let's say we wanted to do it algebraically. 2 factorial is just 2, so we can move that to the other side by multiplying both sides by 2. Next, n factorial is larger than n minus 2, so I'm going to peel off terms from n factorial until I match this factorial in the denominator. So for the numerator, I have n times n minus 1 times n minus 2. Now, this is as far as I want to go, so I'm going to leave the factorial here. One mistake I keep seeing students do is giving each one of these a factorial, but that would change the question drastically. Divided by n minus 2 factorial. So now these two cancel out. And we're just left with this part here. And this is 56. So multiply this out, collect it onto one side, and we get n squared minus n minus 56 equals 0. We can solve this one by factoring as well. So we'd have n minus 8 and n plus 7. And that would leave us with n is equal to 8 and negative 7. And we don't want the negative 7. It would be extraneous in this case. This was part of Permutations, Combinations 1, 2, 3. Here are some questions from the textbook. Try them out, see if you know what you are doing.